Hey everybody, so in this video I'm going to show you real quick how to solve systems of equations using several different techniques. First starting with a technique called Cramer's rule, and then also with your TI-89, TI-84 calculator, and MATLAB. So, usually when we're doing some kind of analysis of a circuit, like a nodal analysis or a mesh analysis, we get some system of equations that has a certain number of unknowns in it, right? So if we have a system of equations, say from a nodal analysis, where we have two unknown node voltages, we're going to get two equations that look something like this: A1 plus V times V1 plus A2 times V2 equals B1, and then a second equation, maybe A3 times V1 plus A4 times V2, and that equals B2. And where these A sub i's and B sub i's are constants, and the X sub i's are variables that we need to find. The V sub i's in this case. V sub i's are variables that we need to find. And so, if we were going to write this in a matrix equation, which I know most of you have not taken linear algebra, so you're not very familiar with this, but matrix equation typically looks something like AX equals B, and for this system, that's going to be something like A1, A2, A3, A4 in a little 2 by 2 matrix multiplied by the V1 and the V2, and then that equals this little vector, which is a 2 by 1, which has the B1 and the B2. Okay, so if I want to solve for these variables V1 and V2, one way to do that is with Cramer's rule. So Cramer's rule goes like this. The values of those variables V1 and V2 are just given by the ratio of the determinants. So if I need V sub I, I'm going to take the determinant of the matrix A sub I divided by the determinant of just the matrix A, where this A sub I is the matrix formed by replacing the ith column of A by that vector B. So in other words, it looks like this. So my V1 in this case is going to be the determinant, where if I'm looking for V1, then I'm going to replace the first column of A with that vector B. So in other words, I would write B1 and B2 here, and this would still be A2 and A4. And then I need to divide that by the determinant of A, which is just the matrix A1, A2, A3, and A4, right? And if you remember how to do determinants in a 2 by 2, this is just B1 times A4 minus B2 times A2, and then that's divided by A1 times A4 minus A2 times A3. However you want to write that, obviously. Okay. And if I wanted to find the V2 here, I need to take the determinant where I'm replacing the second column with the B1 and the B2 vector. And then, of course, that's still divided by the normal A matrix, A2, A3, and A4. Okay. So obviously then I have A1, B2 minus A3, B1 over the determinant of A, which is still A1, A4 minus A2 times A3. Okay, that's one way to do it with Cramer's rule. Now, for systems that get bigger than this, obviously then you have to take the determinant of larger matrices, and so this little cross multiplication subtraction rule for 2 by 2s doesn't work. And in that case, you're going to want to start, finding the determinants on your calculator. But if you're going to use your calculator or MATLAB, let's say, it's probably just easier to just solve the full system of equations and pull whichever variable out that you need from the start. So in other words, I'm going to start, and I'll just do this with a simple example here. I'm going to create a system of equations actually that looks like this. I'm going to have 4v1 plus 3i2 equals 6. And again, so this wasn't from necessarily like a nodal analysis. Somehow I did an analysis and I ended up with two equations and two unknowns. The second equation is going to be 2v1 minus 1 I2 equals 4, right? So those variables don't all have to be voltages. They don't all have to be currents. It can be whatever mix of unknowns that you need, as long as your equations were written, you know, using KVL, KCL, mesh analysis, nodal analysis, and as long as they are correct, okay? And you get a certain number of unknown variables and a certain number of equations in order to solve for those variables. So this is my example system of equations here, okay? And so I'm going to convert that into a matrix. So my matrix is going to look like 4, 3, 2, minus 1. And then I'm going to have V1 and I2 as those output variables. So this is my matrix equation, and 6 and 4. Okay, so what we're going to do next is solve these on the calculator and in MATLAB, just using a direct solution method, either the equation solver or what we call reduced row echelon form. So if you've done any kind of linear algebra, you know that basically what you can do is try to do some kind of algebraic manipulations to combine this A matrix, the 4, 3, 2, minus 1, and then the 6 and the 4. This becomes a 2 by 3 matrix, okay? 2 rows, 3 columns. And you do some algebraic manipulations in order to get this into another form, which is going to have 1, 0, 0, 1, and then some number here, and then some number here in the final column. And so if you're looking at this, this is going to be the solution value for V1, and then this one is going to be the solution value for I2. And by the way, I'm doing this example with real numbers, but you can use phasors in every single one, or complex numbers in every single one of these positions as well. And if we need to make another video showing how to do that, I can. But anyway, let's jump to the calculator and go ahead and plug in this system of equations. Okay, so here I am on basically an app I have on my phone that emulates a TI-84 Plus, or at least awfully close, approximately. And there's several ways to do this on your TI calculator, on your TI-84 particularly, right? First of all, maybe the easiest way is right down here in the bottom right corner. It says entry in blue and solve in green. If I hit alpha, the green button, and hit enter, it goes into a solver, okay? And for this particular example, I don't have a polynomial, right? I have a system of equations. So I'll go down here to my system of equation solvers, and then option 8 says solve system equations, two unknowns. And if I tap on that, it brings up this matrix, right? Which is a 2 by 3, okay? And all I need to do is plug in my coefficients. I'm going to go 4, and then 3, enter, and then in the third column there I have a 6, and then back to the first column 2, and then a -1, and then a 4. Boom. Okay? And that comes out with, okay, my numbers on this solution are V1 equals 1.8 and I2 equals -0.4. Okay, great. That's one way to easily solve this. Now, the only issue that I feel like I see here, I'll hit clear to exit out, is that when you do that solver on your TI-84, and I could be wrong here, it goes 3, 2, 3, 4, and 5. It doesn't have like a larger number than that. That's not going to be a problem usually for us, but in the future, if it is, there's a different way to do this, and that is to go to the button that says second matrix. So in other words, where the x to the -1 button is over here in the center left, there's a blue thing that says matrix, and so if I go second matrix, it pulls me into the matrix menu here. Now you can see I've already defined a matrix A that's 2 by 3, and if I hit the little edit button, I pull into that 2 by 3 matrix, and I can just define my matrix A as being a 2 by 3 matrix that is 4, 3, 6, 2, -1, 4. Okay, great. So I've got my A matrix there. And what I do from there is I'll just quit that and go back to second matrix, and I go to math. Okay. And if I use the RREF function, okay, then I can go back to my matrix and reduce row echelon form of that matrix, and it comes out to 1, 0, 1.8, and 0, 1, minus 0.4. And so I got the same answers. I got 1.8 and minus 0.4 for V1 and I2 in this system of equations. Okay, so that's how you do it on the TI-84. You've got an actual solver, or you've got the reduced row echelon form. And if I go back to my matrix menu here, you'll notice under math I also have the determinant of a matrix. Well, I can't take the determinant of a non-square matrix, so I can't take the determinant of this 2 by 3, but if I had my 2 by 2 matrix that was the 4, 3, 2, minus 1, you know, I could be taking determinants and applying Cramer's rule that way if I wanted. But I think, personally, I think it's always easier to just go with reduced row echelon form. So on the TI-89, it's much the same, but a little bit different. So here I'm pulling up my TI-89, and the way that I usually do this on the TI-89, and I think actually you can do this on the 84 as well, and it's basically the same format, is I'd usually go to the catalog and pull up the RREF command. And as you can see, it gives you right underneath where my command line is there, it says mat, and then there's a square bracket, and then comma tall, and then a square bracket. But basically you need to enter the matrix here, and the way you do that is with square brackets. So I'm going to reduce row echelon form of this matrix that I have, which is 4. And then you can either use spaces or commas. I'll just use commas. I like using commas. 4, 3, 6. And then to delineate different rows, you need to use like a semicolon. So there, 4, 3, 6, and then semicolon, 2, -1, 4. And then second, close that up with a square bracket, close that up with a parenthesis, and I've just reduced it. Oh, and it came out to 9/5 and minus 2/5, but let me make that approximate using the green diamond button there. 1.8 and minus 0.4 for my variables V1 and I2. So it works, okay? So that's how to do it on the calculators. Obviously, you know, you can also do, on the TI-89, you can also do determinants and all that, and you could apply Cramer's rule. But for me, once you have your correct system of equations and your unknowns, it's just easiest to write the matrix and just solve them all and pull out whichever ones you need. Okay? Okay, so the third thing I'm going to show you here is doing the same thing in MATLAB. MATLAB, I don't know if you all know this, but you all through Boise State have a MATLAB online account. And so you can go online to MathWorks and log in with your Boise State email. And set yourself up an account. It's free, right, through Boise State to have MATLAB running right here on your browser. Okay, so here's my browser and MATLAB, and I can tell you, it looks like my Camtasia is not quite recording the whole thing, so I'm gonna scooch it up and see if I can do that. Okay, and hopefully you can kind of see what's going on. But here in MATLAB, it's the same exact commands, even the same exact format. So the first thing I need to do is create that matrix of my coefficients and the stuff on the right-hand side of the equal sign. And I'm just going to call that matrix A, of course, because that's what we've kind of been calling it. And same thing, brackets. I'll use spaces here since it's a little faster. 4, 3, 6, and then semicolon, 2, space, -1, space, 4. Okay, and if I don't use a semicolon on the end and I hit enter, okay, there's my A matrix, and notice it saves to my workspace, and it's a 2 by 3 with 2 by 3 matrix with those values. And now all I have to do here is RREF of A, and boom, there it comes out. So my V1 was 1.8 and my I2 was minus 0.4. Okay. So that's how to do all of this stuff, you know, very simply, very easily, solving systems of equations in MATLAB, in your calculator. And like I said, you can still do complex numbers, and maybe I'll have to show you that in another video. But I don't want the solution of these systems of equations to be a stumbling block. We have computers and technology to do it. The hard part, maybe for you in the circuits analysis class, is getting to the point where you're confident that you have the right system of equations to solve. And through doing nodal analysis, mesh analysis, KVL, KCL, or whatever it may be.